So we have the mass number of elements such as carbon 12 having a mass number of 12, carbon 13 having a mass number of 13, and carbon 14 having a mass number of 14. However, the real mass of the element is the average of all the atoms' masses. If you find a sample of, let's say, coal, the black coal, a rock, you would have all three kinds of atoms of carbon: carbon 12, carbon 13, and carbon 14. One weighs close to 12, the other weighs close to 13, and the last one weighs close to 14. And the unit is atomic mass unit, AMU, which is the mass of a single atom. But how much carbon 12 do we have? How much carbon 13 do we have? How much carbon 14 do we have? If we know the percentages, the relative abundances as we call it, then we can actually calculate the average mass of that atom or of that sample. For example, to make things simple, let's say we have some hypothetical element X, and X occurs in two different isotopic forms, X10 and X11. Now obviously, if we say 10 and 11, they would be something that could be from the first 5 or 6 elements up to boron, but we will just assume that this is some new element with mass number of 10 and mass number of 11. Also, we have one more piece of information. Let's say that 61.5% of all the atoms in the world that X is found in, 61.5% are made up of X10 with the mass number 10, and the remaining, remember the percentages must always add up to 100. The remaining 38.5% is the atoms which has the mass number of 11. Now, had all the atoms of X been X10, meaning mass number 10, then we could say that the mass of a hypothetical atom of X is close to 10. Similarly, if it was 11, we could say it is close to 11, but it's not the case here. Since it's composed of two different kinds of atoms with two different masses, we need to take the average, and the average we will take is called the weighted average, where we will not simply add up the mass of each. Let's say the mass of the first one is 10.0 AMU, for example, right? 10.0 AMU, and the mass of the second one is 11.0 AMU. We will not be simply saying let's add up 10.0 AMU plus 11.0 AMU and divide it by 2, getting 10.5 AMU. That would be a simple average. In a weighted average, what we do is we multiply the mass of each isotope by its relative abundance fraction. So the relative abundance of X10 is 61.5%. In fractional form, you divide it by 100 and you get 0.615. So we do this, and we do the same for the other isotope, where we multiply its mass with the relative abundance fraction, which is 0.385, and we simply add the fractions up. Let's do that. Let me open my calculator and let's see what comes out of this. Always pay attention to sig figs, and I get 6.15 AMU for the first isotope, and for the second one to 3 sig figs I get 4.24 AMUs. And now I simply add them up and I get 10.39 AMU. So this is the average mass of the hypothetical element X. Notice that if I had simply said let's add 10 plus 11 and divide it by 2, I would have gotten 10.5. But instead I'm getting 10.39, closer to 10 rather than closer to 11. Why is that? Because we have greater amount of the isotope with the mass number of 10. So the final outcome is weighed closer towards that particular isotope. And this is why we must take weighted average, because we don't have equal amounts of the isotopes. And you may have more than 2 isotopes. You may have 3, you may have 4, you may even have 5 isotopes. What do we do in that case? Simply the relative abundance of each isotope as well as the mass of each isotope must be provided, and you simply multiply the fractional form of the relative abundance of each isotope with their individual masses, obeying the significant figures rules, and the outcome you add them all up and it should give you the average atomic mass.